We are live.
Bună seara! Suntem live din ce văd din aceste setări de tehnice, așa că trebuie să vă urez și sunt bucuros să vă urez bun venit la o nouă discuție cu Jim Baggott, unul dintre autorii mei preferați și ai românilor și ai editurii Humanitas de cărți de popularizare a științei. De data aceasta, în seara aceasta, ne întâlnim pentru a vorbi despre noua sa carte, Masa, o carte de fizică, de istoria fizicii și inclusiv de filozofia fizicii, despre acest concept aparent intuitiv, masa, dar extrem de și complicat și interesant. Pe Jim Baggott îl știți din conferințe, a vizitat România de mai multe ori și ca jurnalist de știință, ca blogger de carte, de fapt, vă pot și vreau să vă îndrum în special către penultima sa carte publicată în România, Origini, o istorie a științei absolut minunată. În curând vom trece pe engleză, evident, pentru discuția noastră cu Jim Baggott despre noua sa carte, așa că sper să-mi tolerați accentul, sper să vă bucurați de discuția și dezbaterea și inclusiv de umorul care urmează, căci Jim se pricepe foarte bine la relaționarea cu media și vă promit inclusiv că vom avea și transcrierea acestui eveniment pentru cei care iubesc textul și cartea. Într-un cuvânt și într-o concluzie, sper să vă placă. Now, switching to my weird English, let's say, I'm gonna say the same things. Welcome, Jim Baggott, for another talk in Romania, a country that you visited and you're affectionate to, let's say, because you really enjoyed, including our talks, because this is my third or fourth interview with you.
Yes.
You're a very appreciated author in Romania, and I'm not kidding about this, because you have a lot of your books translated into Romanian at Humanitas, and in my opinion, you're one of the best historians of science that we have access to. Your latest book, again, Mass, is a history of science about a topic that most of us could raise a brow and say, this is a whole book about mass. Why is it so fascinating and why it's necessary? Because we don't really know a lot about the conclusions, the scientific conclusions about the scientific quest for the answers of mass.
Okay, so let me explain a little bit the background as to how I came to write this particular book. And it's funny, I was reminded not so very long ago that shortly after I graduated with a degree in chemistry at the University of Manchester back in the 1970s, when most of your audience, I'm sure, were yet to be born, I had an idea that it would be really good to write a book about the history of atomic theory. So our understanding of atoms right from ancient Greek philosophy through to the present day. And of course, that was naive. I was young, in my early 20s. I didn't have the wherewithal to sit down and write a historical book like that, although I did start to read about ancient Greek philosophy and the atomists at that early stage. And it was really writing and experiencing the discovery of the Higgs boson at CERN in 2012, and then subsequently writing the book, that made me realize that if you have no scientific background whatsoever, that doesn't prevent you from having an intuitive idea as to how the world works. I mean, you understand, you get on the bathroom scales in the morning and you weigh a certain amount, and you know you deal with aspects of Newtonian physics in your everyday lives. So you don't have to have a scientific training to understand the concept of mass, I don't think. Now, there are some subtleties. If you were, like me, entranced by the early moon landings in the late 1960s, the sight of American astronauts bunny hopping on the moon because of low gravity, and the realization that if they made a sudden movement, they could very easily overbalance. And of course, it was very dangerous if they fell over on the surface of the moon, because they ran the risk of damaging the suits that were protecting them from the very hostile environment that they were in. But this was the realization, quite simply, that your weight on the moon because of gravity is still not the same as your mass. So when you make a sudden movement, you have suddenly all that mass to deal with. And it's disorientating because you're used to your mass being equivalent to your weight on Earth. But when you're on a different planet, it's not the same set of forces. So stuff like this, we become familiar. And the one thing that I think I learned as a result of understanding aspects of modern particle physics and the way that the set of elementary particles in the standard model fit together was this understanding that the concept of mass had gone, basically. It had been replaced by the idea of energy and forces between particles, in this particular case, between quarks that sit inside protons and neutrons, which sit inside the nuclei of all atoms. And I felt that was an interesting story, this very simple notion, which you can easily use the ancient Greek philosophers to explore. It's kind of common sense, really, all the way to completely unraveling this idea of mass in modern particle physics was, I thought, an interesting tale. How did we come to get here from some very intuitive, very simple, very straightforward ideas about what we think mass is? So that was the origin of it. And it was just a question as to whether I could write a book that was sufficiently compelling.
Knowing your other books, I really do think that you are enjoying the travels through the history of science, because you start with the ancient Greek philosophers, and the reader and myself have this reaction that, yeah, I know this. Why do you keep telling us about dead ends? And then those dead ends come up again in modernity, in the recent times, that we pose the same questions in different words, or sometimes same words. How frustrating or enjoyable was this travel through history?
Well, I've as a result of everything, I think broadly everything that I've written over the past 20 odd years of writing about aspects of physics and chemistry, I've come to a conclusion that if you promise not to tell anyone, I will reveal to you, but you have to whisper it. And that is that all our ideas of modern physics, modern chemistry, and even to a certain extent biology rest on some fundamental notions or understanding, if you like, of space and time, matter and light. Those four things compose everything in the universe, everything we understand as far as we can tell, although there are some huge gaps which I can elaborate on if required. But space and time and matter and light are the fabric, I use that term in the book, that effectively we then paint pictures on. Our ideas about how the universe works, and galaxies and stars and atoms and people and planets and all sorts of things are painted on that fabric, that canvas. And the conclusion I've come to is that we still don't understand space and time and matter and light. And I feel that in 2,000 years' time, we could have obviously a way more elaborate meeting than a Zoom meeting, where someone who's written a popular science book will tell you we still don't understand space and time and matter and light. Now, our understanding of these things has advanced, of course, but it depends on who you want to talk to. You will find that there are still way more questions that we can't answer about these fundamental things. The answers that we can give, rudimentary though they may be, are enough to build huge particle colliders, enough to build the technology that we all use, our smartphones, satellites, streaming TV, whatever it might be. We've sophisticated enough understanding to do all of these things, but that's still painting on the canvas. It's still painting on the fabric. And without really understanding the fabric itself, we can still go quite a long way. So I love to tell the story of how far we've come, but I would hope that I'm not a triumphalist. There are certain scientists that like to suggest that in science has all the answers. And certainly when it comes to these fundamental aspects of the way nature is, it certainly doesn't have all the answers. It has lots and lots of questions. And I find that for me, myself personally, to be way more interesting than having lots of smug answers.
You just stole my next question, because I was even if the term is dangerous, the idea of scientific progress, the fact that we got ourselves in this fog, scientific fog, in quantum physics, for example, it's also a progress, because we actually, the fact that we realize that we don't know a lot of stuff is actually the next step to finding it.
Yeah, I think it's like acknowledging the nature of the problem. Before you can acknowledge the nature of the problem, before you can, search for a solution, you need to acknowledge the nature of the problem. And that's often easier said than done. So in the case of quantum mechanics, which again is a fundamental part of our understanding of the whole story of mass, we're at a situation where I think we have an excellent theory that really, really does work. But we've hit a buffer because to a certain extent, we can't agree what the theory means. And that sounds crazy, because how can you use something if you don't know what it means? But trust me when I tell you, you can use quantum theory as an instrument, as a mechanism. You plug some numbers in, you get some numbers out, and it works. And that's fantastic. But without knowing what it means, there's a limit to how far we can now go. And there's a limit to how we choose to look for the next advance, the next layer of understanding that I know lurks underneath quantum mechanics. But quantum mechanics as a theory was established 100 years ago, and we've not found any way to transcend that yet. So I think it'll be a few more years yet before we get a breakthrough where we say, okay, well, this is indeed the next shift. This is the next layer of understanding. And whether that'll be understandable is another question. Whether the meaning will be any more clear, we might have a better theory. The numbers are more precise, or we can do things we couldn't do before. But maybe we've reached the threshold of where we can actually say we understand. We can do some things, but we don't necessarily understand. And I find that fascinating. And that's what drew me very early on when I discovered that as a student at university. That's what drew me to look at the philosophy of science, because you can't really understand the nature of the debate about something like quantum mechanics without understanding something of the philosophy.
You said the same thing in our last interview, that the fact that physics right now, I'm trying not to offend you, but you said physics right now is a swamp. But for a kid or a new student going into physics, theoretical physics, it must be exciting, because you must think of yourself, maybe I can find maybe not an answer, but a thread, a new thread that will lead to new physics.
Yeah, that's that's definitely possible. And of course, I would want to encourage anyone who feels that that's something that they want to devote their life's work to. But there are a couple of things that anyone going into that, charging into that field should be aware of. And the first is the nature of the sociology of science. And it's pointless to try and pretend that doesn't exist. So there are fashions, there are trends in theoretical physics, just as there are fashions and trends in any other aspect of human endeavor. And the dominant fashion at the moment is still very much string theory and supersymmetry, if these are terms that you're familiar with and you've heard of. And it's quite difficult, I think, for a young idealist to come into a field where, by definition, if they're trying, string theory has made no real progress in nearly 50 years. So if you're wanting to challenge and find something and maybe make a breakthrough, I would respectfully suggest that it's not going to be in the string theory community. So you're going to be outside of a fairly large and dominant community in theoretical physics. And let's be clear, it's tough, it's difficult. I've written another book. Whether this will be published also by Humanitas remains to be seen. I cannot remember now whether Humanitas has purchased the translation rights for it, but it's a book about an approach to joining together quantum mechanics and Einstein's general theory of relativity to make what is effectively a theory of quantum gravity. It's called Quantum Space, and it's about loop quantum gravity, which is effectively the brainchild of a couple of perhaps well-known theorists, Lee Smolin and Carlo Rovelli. Carlo Rovelli in particular has become very, very popular because he's written some great popular science books. And these guys for a long time were outsiders. They were very much outside the mainstream, even though there was a lot of overlap between what they were doing and what the mainstream string theory community were doing. And you just have to accept, you have to look, you have to be pragmatic. So the science is one thing. You have to remember this is science as done by human beings, and human beings being human beings will find a way to make it a little bit more difficult or a little bit more obscure or a little bit tricky to be able to do what you think you want to do.
You mentioned those fashions, intellectual fashions, but they are still on the cover of most science magazines. So
yes,
we still have a few years to go before they're, let's say, not only abandoned, but at least reconsidered. And you also mentioned Carlo Rovelli, who's a great poet, but in a good way of science. And he really tries to translate and to use metaphors for us, non-physicists, to understand physics. But his latest book, absolutely wonderful, Helgoland, made me cry. Coming back to you, your books also sometimes they're not going to make me cry, but they're going to make me reread the chapter. So let's talk about the honest approach of not really watering down the physics, but really trying to explain them.
Yeah, so I trained as a scientist. So you will see me publicized as a popular science writer, and that's fine. I'm happy with that. But I trained as a scientist, so my background is in science. I was a university lecturer for many years. Did my PhD at Stanford University in California in chemical physics. So I've got a scientist's mindset. But when I left academic science and I went off in a different direction, I decided that I wouldn't leave science behind completely. And then writing articles and books was the way that I would keep in touch, as it were, or stay part of a scientific fraternity. But I set myself an ambition. Physics it's hard. Now, I don't want to sound discouraging, But seriously, it's a hard science. It requires a heavy and detailed understanding of mathematics to make any progress. And it deals with some very, very obscure concepts. Again, if you want to work on the front line in theoretical physics, you're going to have to do your 10,000 hours, however you want to think about it, in some very, very difficult subjects. And I looked at some popular science books, and in their efforts to communicate the essence, and many of these, don't get me wrong, were really excellent books, great communicators. But what they'd done is they'd stripped the difficulty out. And I'm not against that. But what I am interested in doing is in stripping the difficulty out, you lose a lot of the meal. You take what is a very, if I were a chef and I'd put together this fantastic meal with lots of balanced flavors and textures, popular science communicators can often take most of the meal away and leave you with something that is palatable and it's nice, but it's not the meal. And what I wanted to try to do is to put some of that physics back in so that people would, they not necessarily understand it even, but they would have a sense that it's complicated, but I think I can get my head around that. And your reaction is exactly the reaction I would be hoping for, is that you'll read a chapter and you'll go, what? And you'll go back and read it again. And then maybe with a second reading, you get a sense, well, yeah, I begin to see now what these guys are saying. And certainly the more simplified popular science books should be easy to get your head around if they've been written well. So that was always the ambition.
I was thinking, also watching your lectures to students where you try to be funny and engaging with them.
Don't always succeed.
From some of them, you get a reaction. I was thinking that I'm a nerd, so I really enjoy your books, but how can I make them interesting at the cocktail party or in a discussion with friends? So yes. I try to make it personal. I had an unfortunate but fortunate in the result, an accident. Somebody ran through a red light and hit us. And that's math for you and all the definition it implies. Do you get the same thing, or of trying to explain the concepts to your friends and colleagues?
It can be done. It can be done at a certain level. If you're trying to explain some aspects of physics, then yes, you can use these analogies, and it's something that I certainly have done and will continue to do. If I'm at a party or I'm in a discussion in the kitchen and someone asks me a question, I'll try and reach for an everyday example as a way of answering. The challenge often comes is when people just want to go deep into something like quantum mechanics, which you can begin to explain it and articulate it, but before you know where you are, you're an hour later, having sunk very many beers, and you're still at the level of not quite yet getting to what they're really interested in. Is why is it so bizarre? Why is it so crazy? So it's trying to build up that understanding, so that you don't just, you can say, look, it's just crazy, and everyone will go, yeah, quantum mechanics, that's crazy, yeah. But understanding why it's crazy, to the point where Albert Einstein got worked up about it and had lots of things to say about it, like God does not play dice and all of those great phrases. They're really good to be able to understand in the context of understanding why quantum mechanics is so crazy.
I was listening to one of your lectures, and you said that quantum mechanics is madness and confusion, but your tone was really happy about it.
I think because, again, it makes it, well, firstly, it makes it interesting, and it's a universal acknowledgement that a popular science book with quantum in the title will almost certainly attract attention. It may not necessarily sell thousands of copies, but it'll attract attention. And there's a reason perhaps my last 4 books have had quantum in the title. But the point about it is, as I say, that it's not enough to write a book and say, look, hey, quantum mechanics is crazy. It's really important for me fundamentally, and there are books like that you can read, but it's important for me fundamentally to explain why, and explain why people like Einstein, Niels Bohr, Erwin Schrödinger, Werner Heisenberg, Wolfgang Pauli, and the things that they had to say about this way back in the 1920s and 1930s. So the arguments that we are still having today about what quantum mechanics means were had by these guys already 100 years ago, nearly 100 years ago. So understanding that too, I think is fundamentally interesting. I've been working most recently on a new book with a very, very esteemed science historian called John Heilbronn. He's written actually an excellent biography of Galileo. If you were talking to Mario Livio, I'm sure Livio would have known Heilbronn's book. And I'm working with him on a book called Quantum Drama, which is effectively the drama of quantum mechanics from the 1920s through, not quite to present day, but really getting into the personalities and the clashes and the arguments back and forth over decades. I think for me, it's, and of course, the real history, or at least what we can get to as close as possible to the real history, is not the superficial history you tend to find in a lot of popular books. And it's really opened my eyes. It's been a real great project for me to be involved with, and John is a great collaborator.
In another Humanitas interview and talk, Jim Al-Khalili was mentioning that in one of his shows, he was interviewing Peter Higgs, and he asked the question, can you summarize, can you explain, can you reduce your findings and research in a minute or 30 seconds? This is gonna probably backfire, but can you also reduce, can you say in 30 seconds or 1 minute, what mass is all about?
What the book is all about. So in 30 seconds or less, the book is about the unfolding history of our understanding of the idea of mass, from the ancient Greek philosophers to modern particle physics. And as you've probably understood from the conversations that we've just had, what you take to be the everyday understanding that you will undoubtedly have about what mass is, has, in terms of fundamental particle physics, has gone in a kind of puff of smoke. What we're left with is energy, and everyone is familiar with Einstein's famous equation E = mc squared. What you might not have done before, but you can easily do in your head, is rearrange that equation to m = E divided by c squared. And what that tells you is that mass, our idea of mass at the level of elementary particles, is energy divided by c squared. So mass is energy, basically. And what we learn is that what we take to be very straightforward and intuitive ideas of where mass resides in the nuclei of atoms, it turns out when you go inside those nuclei and you're dealing with quarks and particles called gluons that bind them together, what you find is the mass is no longer in the quarks. It's actually in the energy created inside these particles by the gluons moving back and forth. And that's mass.
Yeah, I think, although I'm not a very good judge, but I think you nailed it in a let's say, in a very good soundbite.
I gave it my best shot.
Yeah. Is this search a purely theoretical one, or as you said, quantum mechanics works and is applied, and every new research also has applied effects, let's say.
So, so the answer is kind of yes and no. It depends on what you mean by applied. So, in this understanding of the standard model of particle physics, which is effectively what I've just explained, the one missing ingredient, by the way, was I saw a question that came up: is how does the Higgs boson work, or the Higgs field? Well, the Higgs field is required in order to give particles mass to begin with. The problem is that quarks gain mass through their interaction with the Higgs field, but that's still not enough to account for the mass of a proton or a neutron. You need the energy of the gluons, as I mentioned, to make up the difference. But this understanding is verified in the sense that we have experiments conducted at CERN and at other big particle colliders like Fermilab in the US and elsewhere. This gives us some sense of reliability, that the theories are telling us the truth insofar as we can get a handle on it. These theories are not applied in the sense that we apply them to make the kinds of, to have an impact on our daily lives, for example. So all of the technology that I just mentioned really comes from understanding of other fundamental theories like relativity and quantum mechanics. You can't use global positioning satellites, for example, without an understanding of relativity. And you can't build electronic circuits and semiconductor technology without an understanding of quantum mechanics. So that gives you some sense. These theories are vital, but the standard model of particle physics is a structure that is verified, but it is not applied in the sense that it's making a difference to the way we live our lives.
I have a question from the audience here that kindly asks you to explain more about string theory. And I can... String theory, yeah. I can infer that he may want to... She or he may want to hear more about your critiques about it.
Okay, so string theory was developed in the late 1970s. What it is it's a response to the challenge of going beyond our current understanding. So the standard model of particle physics that I've mentioned a couple of times it's a wonderful structure. It's built on what are known as quantum field theories. So this is our understanding of quantum mechanics elevated to the level of fundamental particles and forces. But it's unwieldy. It comes in three pieces that don't join up. And string theory was an attempt to go beyond to that, to something even more fundamental. The problem with a theory about particles and fields is that the particles are imagined to be or considered to be point particles. So they effectively have mass, but they have no spatial volume. They occupy no space. They're ideal, if you like. And the idea of a string was to say, well, what if we have a two-dimensional object, like a string that vibrates, and maybe the vibrations of the string will give rise to the properties of the particles that we can discover and follow in a particle collider. The problem was it ran into serious difficulties. You needed lots and lots of spatial dimensions, 26 dimensions for these strings to vibrate in. That got cut down to 10 dimensions if something called supersymmetry was assumed. That's a fundamental symmetry between particles called fermions, like an electron, and particles called bosons, like the photon or the Higgs boson. If there's a fundamental relationship between these particles, which there could well be, then superstring theory then started to become the first choice. And a lot of effort was put in. If you're going to have extra spatial dimensions that you don't know what to deal with, then the mathematicians then say, well, we'll compactify those, we'll fold them up and hide them away to a tiny little space. And that's the manifold is known generally as a Calabi-Yau manifold. It doesn't matter what that means, but it's a way of hiding away the extra spatial dimensions that superstring theory needs. Then the problem was there was no unique Calabi-Yau manifold that would do the job. Nothing that could predict the particles and forces that we know exist in our universe. And so this went on. Every solution led to loads and loads more problems and could only be solved with more and more assumptions. So the theory, in my view, got further and further and further and further away from even remotely being tested. If you tried to test it and a prediction was not upheld by an experiment, well, you just go and change the number of dimensions, or you change the manifold, or you change this and you change that. That for me is not a testable theory. It's slipped. It's become a fog, something that's you can't get your hands around, your arms around anymore. And it's got worse. One final conclusion is that these problems, some very esteemed theoretical physics, I won't name any names, have gone even further and said, well, all of these problems can be swept away by saying that we actually live in a multiverse. And each different Calabi-Yau shape that we cannot predict defines a different universe. And we just happen to live in the universe that can support intelligent life. Well, if that's not really touching the question, then that's where I lose it completely. That's where I'm saying you've produced a theory that's no longer testable. That's not physics in my view anymore, even though it's a very, very big community and there are some very, very esteemed theoretical physicists who declare themselves to be string theorists. But in a nutshell, that's the problem I have with it.
And that means that we can dare to say they're dead ends?
It's difficult to know. I don't think science doesn't work logically, and it's if you're a non-scientist, it's difficult. That's a difficult statement to accept sometimes. When you've got people who've dedicated their entire careers to a theory that's clearly, from an external viewpoint, not going anywhere, you find it very difficult to persuade them to think differently. And quite often what happens is that the theory itself doesn't get abandoned until something better comes up. And at the moment, there is not too many choices as to what is a better alternative to string theory. We're waiting for that new generation of young and inspired theorists to come along and challenge the status quo. Or some of the older generation. There are one or two Nobel laureates in the string theory community. And again, I don't want to sound morbid, but when they die, the momentum of that program will start to fall away. They'll no longer be pushing for grant applications. They'll no longer be getting funding. And so what tends to happen is that these theories don't themselves die. They kind of just fade away. And I think that's what will happen to string theory. It may take another couple of decades even, but string theory, I think, will just fade away.
We often forget how science is blended with psychology, economics, and
sociology.
Sociology, exactly.
Oh.
And another question that may be annoying, because I know it's not A or B, the next generation should go to the blackboard or to another even bigger collider?
Really difficult to answer that question. I think the building of another bigger collider at CERN is probably inevitable, but I think the lesson that was learned with the Large Hadron Collider, I hope, will be remembered. When the Large Hadron Collider was being built, there was a lot of hype about how it would find the Higgs boson, find evidence for supersymmetric particles, which is what superstring theory needed to have in order to show that it was a valid approach, find other exotic particles that I've not mentioned it, but our theories of cosmology demand something called dark matter. Don't ask me what that is, because nobody knows. But there was hype that the Large Hadron Collider would find evidence for dark matter particles, and so on and so on. And I think all that the Large Hadron Collider has revealed is the Higgs boson, nothing else. So I think it's going to be harder to justify the next generation of particle collider, but I think it will be justified, because frankly, we don't know what else to do. That's not, by the way, a good argument for spending lots of taxpayers' money building a fantastic piece of machinery. My hope is that you'll build a machine that doesn't look or is not hyped around finding new things, but it's doing what science always tends to do. Once you've made a discovery, you dig in, you investigate, you improve the precision, you explore what the Higgs boson is. I mean, it's now we know it's there, it's real, but who knows what its real properties are? So we get in, and this is not as inspiring. It doesn't create the headlines that often the public need to justify the amount of money that's being spent on it, but it's what science does. It gets into the weeds, is a phrase. And one hopes, my hope is that by getting into the weeds, you'll make a discovery that's shocking and surprising, and you'll say, whoa, wasn't expecting that. And it's through that kind of situation that you might then get some clues as to where you need to develop the theories next.
Do you expect, or what are the next twists in the story that you expect in the story of mass?
I'm not entirely sure that there is a next story, because I don't see quite how you can go beyond the conclusion that there is no such thing as mass. So effectively, mass as a familiar concept has disappeared. That's why the final chapter of mass is called Mass Without Mass. It creates a behavior. So at the level of, at least of fundamental particles, mass is no longer a property that particles have. It's a behavior that they exhibit under certain circumstances. And for me, the best way of thinking about this is to actually go back to the iconic experiment in quantum mechanics, where you push electrons through a two-slit apparatus. So a two-slit device effectively is a way of creating interference. If it was light, you'd shine light on the two slits, the waves expand beyond the slits and overlap and interfere, and you get a characteristic fringe pattern. Well, you can do this with electrons, and was really the origin of quantum mechanics, is the realization that particles like electrons also behave like waves. Moreover, you can do it with one electron at a time. And I used to ask myself the fairly logical question, what happens if I imagine the electron as a little piece of matter? You always imagine it as a spherical thing, but a charged particle with mass. I get that it behaves like a wave as it goes through two slits and produces an interference pattern, but what happens to its mass in between? So it's understanding that the concept of mass as something that's intrinsic to matter, it's a property of matter, is no longer helpful. In modern theoretical physics, you have to almost abandon that and say, okay, well, mass is something that then is a behavior. It's something that particles show as a result of some of the things that we get them to do.
One of our listeners wants to take you into the dark matter subject. And
okay.
The question is, dark matter should be the energy of the empty space, 0-point energy, and is there a scientific consensus about this?
Right, so we have to be careful, because there are two distinct, huge gaps in our understanding of cosmology and the structure, large-scale structure of the universe. The first is dark matter, and the second is dark energy. The dark matter, dark matter, the idea of dark matter arose out of making observations on galaxies that rotate. And that if you observe the speed of rotation at different distances from the center of each galaxy, what you find is a puzzle, because you can use Newtonian physics to predict. It's a simple, large scale thing. It's not quantum mechanics you need here. It's you're dealing with lots and lots and lots of stars, billions of stars in each galaxy. So as these galaxies rotate, they were found to have a behavior that could only be explained if there was more mass in the outer edges of the galaxy than appeared from the visible stars in the galaxy. And the only conclusion was that missing matter must be dark matter. Dark matter was then used as a means for understanding how galaxies form in the first place, and it started to become an essential ingredient in our understanding of galaxy formation in the first place, as well as galaxy rotation. Moreover, it's now a key ingredient in the Big Bang theory, the so-called concordance model of Big Bang cosmology. So satellite missions that have gone up ever since COBE in the 90s, the WMAP satellite, the Wilkinson Microwave Anisotropy Probe, and most recently the Planck satellite, have all measured the temperature of cosmic background radiation coming from all different directions in the universe. That can be modeled and give us something of a history of where the universe has come from the Big Bang, but it also tells us something about the composition of the universe. And there's a big piece required that only dark matter can fit, but this is matter. Now, famously, when Einstein developed his general theory of relativity in 1915, he went on to apply it to the whole universe, but found a puzzle, because his theory predicted a universe that wasn't static. It would expand or could collapse. And he didn't like this because he felt the universe, everybody could see it's a static thing. So he fudged his equations. He introduced something called a cosmological constant to keep, it's like a kind of anti-gravity, stop everything from coming together or pushing apart. He abandoned that when it was obvious from galaxy observations from Edwin Hubble, actually, that the universe is indeed expanding. Now, the only problem is that when you look at the rate of expansion, and you look at the rate of expansion as applied to the most distant objects in the universe, we find that we have to put that cosmological constant back. And that cosmological constant represents dark energy. And it's, again, literally like an anti-gravity. It's space pushing outwards, pushing everything away, not in a way that you'd ever observe. You can't see that on Earth or anything like that. We're talking about the large-scale structure of the universe here. So the model that Planck satellite and all the analysis produce says that the kind of matter that we were always concerned about, visible stars, us, planets, is only 5% of the total mass energy of the universe. There's about 27%, 27% is dark matter. And the rest, about 69, 70%, whatever the number is dark energy. So the universe is an interesting place. Only 5% of it is visible. And these are exactly the kinds of conclusions I love about modern physics, because it tells you we just don't know. We just don't know what most of the universe is made of. I love that.
Yeah, you just mentioned Einstein's brilliant blunder, as the title goes, and yeah. I love it that you always have a story, a story of the history of science for every answer. And now comes, I think, the most at the end, the hardest question of our talk, because And you're the best one to answer it, because you spent a lot of weeks and months and years writing books that explain science to the audience. But can the audience really get the science? Can they really get to a satisfying level in all sciences? Because the level is now so high that it may be impossible for a regular reader that has another job, another specialty altogether,
Sure.
to get
Sure.
to understand physics or medicine.
I think it's just a question of your everybody's personal preferences. Not everybody gets fired up about this. Not everybody's interested in these kind of what I call the big questions of existence. You know, what is the universe? Where did it come from? How did life form on Earth 4 billion years ago? However, I think there is always part of us that is compelled by some of these questions, and we'll reach to all sorts of different sources to provide answers to them. But if the source that you're interested in looking at is science, then I think in fairness, there are ways of getting the essence of what science is telling us without too much difficulty, without too much effort. Not necessarily getting into the detail. Again, I would even suggest don't look at my books, look at other popular science books that might be more accessible than mine. I tend to want to give a bit more of an account of the physics. But if you're all you're interested in is the essence, then there are plenty of books on the market where you can get the gist. You can get the gist. And I think that's important both in physics, if you're curious and you want to have some sense of how we respond to the questions, the big questions, from a physics point of view. I also think that certainly in the background of the global pandemic, understanding a little bit more about aspects of biology, virology, there's to a certain extent, there's even almost an obligation to be informed a little bit, so that when advice comes from government scientists, for example, to wear masks or to do this or to do that, you can understand and you can be sympathetic towards what government agencies are trying to do to prevent, to effectively to keep society reasonably safe in the midst of this troublesome virus. I certainly think we need an antidote to science denial. And it's been interesting to see what's happened in the US and to a very large extent in the UK as well, and in some other countries, but it's been Western developed societies that have majored on individualism and the freedom of the individual to make their own choices. That balance has been wrong. And of course, it's been exposed to be wrong by the pandemic. It's one thing to have this sense of individual freedom, but not at the risk of giving up all obligations to society. So finding that balance, again, you can only really do it if as individuals we take responsibility to be moderately educated about some of the things that we're being confronted with. I don't know if that answers the question.
Part of it, and I will have the audacity of saying at the end something that I think is complimentary and also a compliment to your work. I think that the arrogance of some readers or some people that they do really understand science at a higher level gets us into trouble. And my message to the readers, which I'm gonna now afterwards I'm gonna say in Romanian, is that
okay,
go read your books, because even if you don't get every detail or explanation in Jim Baggott's books, at least you get the gist, or you understand how science works. And I think that's even more important than getting some of the equations right or some footnotes right. The most important thing is that you get an idea about the history of science and how we get to where we are now.
Yeah. Excellent.
And now, before we say our goodbyes, I'm going to say it in Romanian. Mesajul meu de final și ceea ce am încercat să obțin și din ultima întrebare și din răspunsul lui Jim Baggott este că trebuie să avem o apreciere a științei chiar mai mult decât o înțelegere a științei. Mai degrabă trebuie să învățăm metoda științifică, cum funcționează știința, decât un bagaj foarte mare de informații. Respectul față de știință și înțelegerea legilor de bază ne pot ajuta mai mult decât înțelegerea detaliilor din aceste cărți, care rămân absolut fascinante și vi le recomand ca istoria științei. Thank you, Jim, and for another interview. I really think I'm going to see you again for the next book. And until
already looking forward to it.
Until our next talk, let's hope we are all healthy and in a healthy society.
Maybe next time in Romania.
Yeah, exactly. Good night. And
okay, good night. Thanks a lot.
Seară bună tuturor.